Okay, and now I realize that I have started recording without. Okay, so let's wait for a moment. Why? Fucking so quiet. Back to. All right. Let's say. There's a short note here and out. You can go and read. I use do this. Okay. The instruction standing of the structure. Okay. Um. This is not difficult to understand. Externally indeterminate and internally indeterminate. I have already shown you both. Okay. So for a typical structure like this, you have the extra reaction. This is externally indeterminate because the your reactions are external forces. So when you have unknown reactions, you have the externally indeterminate structure. And the internally indeterminate is something that even though you have known your reactions, you still cannot solve it like this. These extra member inside will give you the internally indeterminate. Okay? And now, as I've said, why do we need this? It's because you're going to have smaller forces in your member. And here redundance will give you extra safety, or in the engineering term, sometimes the alternate load path. It means that if something collapses, the load can go somewhere else because of the extra reaction. And force is much more rigid than the simple beam. Okay. Here, the method that you have learned, not have learned, the method that I've discussed in the first hour is officially called the method of consistent deformation. Can you tell why it is called consistent deformation? It's consistent deformation because now we have to say that the deformation caused by the external load must be equal and opposite to the deformation caused by your reaction. That's why in order for them to be compatible, they must be consistent. Okay? And that's the guy, James Clerk, Maxwell, and Otto Moore. Otto Moore that has given you your beloved Moore circle. Yeah, like Moore circle is not enough, right? So he has given you another method of consistent deformation. Okay. Now, what we have done, what we have discussed in the first hour, can be summarized into the process like this. Okay, so you can just go on and read this a little bit if you want. Determine the redundancy. Remove the unknown forces to create the primary structure. But you have to make sure that your primary structure is safe and stable. And then calculate the deformation after you remove the redundant. And then calculate, I will go back here in number 4 a little bit, calculate the deformation of the primary structure due to redundant or the reaction to remove. There is something like this that we will go back, okay? And then assemble by using the compatibility. So we have discussed that, and it's right there, you know, summarized nice and tidy, the handout, but generally it's not fun. I don't really go back with that. It's boring, you know, imagining myself coming in to the classroom and, you know, give a PowerPoint to you and read. I don't do that. I'll sick to death myself. I'll be sick to death. But some others might do that if it, you know, if they see it it's gonna be same more beneficial to you. It's possible. You know, I'm not saying that this is the best method. This is what I do. And for some, you know, this class is about calculation. It's almost pure calculation. So you better do this because in the end, it's not useful for you to remember the process, right? We don't memorize this. We put this into you. So in other subjects, you know, doing this might work. Okay. So I'm not saying that those who do not do this not good. Okay. So let's come back here a little bit. Okay. Here, there's another approach to this because let's back this up. Okay. And say, same structure. Okay. So step number 1, determine R. Redundancy, we have 1 redundant. So we can say it's a 1 degree of redundancy. Okay. So the second step, what's that? We remove it, right? So the second step, am I correct? All right, primary structure. Okay. And the third step, we can do it, right? Yeah, maybe. Let's try it. So let's say this is W, this is L. Okay. Say if you can recall, I'm just gonna do it out of memory. You know, it could be wrong. But I hope not. Okay. This is point A. This is point B. If we are going to use the moment area method, the displacement at B is equal to TBA, right? Nobody can. So step number 3 is the calculation of delta B after we remove the redundant. Redundant is now removed. Okay. Now, in order to do that, we need a moment diagram. And the bending moment diagram is, oops. Sorry, I had oops. Oh, okay. So this value is minus WL square over 2. And delta B is equal to TBA. And you need to use the M over I diagram. So I would divide it by I. Okay. So that will come the value of WL square over 2 over I. And this area is parabola, so 1/3, right? Area is equal to 1/3 of the height is WL square over 2I multiplied by the length. That's the area. And TBA is equal to taking this moment area about point B. Correct? The point B here. And the centroid is 3/4 of the length. Hope you all know it. I'm not making this up. You don't believe me? You're gonna have to go figure it out. Okay. So the area is 1/3 of WLQ over QEI. Now multiply by the moment arm, which is 3/4. 3 is 1. So yeah, I think I'm correct. It's WL to the power of 4 over 8. Right? So that's the deflection delta B. So we're done. Step number 4. Step number 4. Now calculation of I don't like the natural straight line in the program being straight. I like actually it is the line you draw, the line drawn by the software. Okay. Here is maybe here's RB. Now we are going to calculate this displacement by RB, which is smaller than now, that's the way. Okay. My phone is here. Please, folks at home, if you struggle to catch up with me, you must let me know, okay? If you stay silent, I will not know. Generally, there are more folks in the classroom, so I can take a look at them and notice them whether or not they can catch up with me. But now it's just only one. So if she is fast, you guys have to. Okay? Let me know, all right? Now, step number 4. We go back here and say, calculate the deformation of the primary structure due to the redundant. By applying the unit force, what do you mean by that? You it doesn't mean, right? What do I mean by that? So some folks will feel that, you know, I don't want to calculate the displacement in terms of RB because before you set up your compatibility, you don't know how much RB is. So you can calculate.
Excuse me, Professor.
On me?
Yeah, I can't hear you clearly.
Oh, you cannot hear me? Okay.
It's better.
But it's okay now, right?
Yeah.
I'm sorry. You know, the microphone is heavy, so I kind of put it down, but it's in front of me. So maybe if I put the microphone down, I'll have to lie down and just put my mouth in the microphone. Got it. Okay. So that's a little bit ugly. So I think I'd rather hold the microphone out. So anyway, you can calculate displacement, whatever we call it, caused by unit load. Unit here means 1. It's a unit load, right? It's kind of, it takes me a while to understand what unit load means. What is this? Is this a load that has 1 load? No, it's a load that is magnitude is equal to 1. They call it unit load. Okay. So you're gonna calculate. You can calculate this displacement caused by the load that has a value equal to 1. That's it. So we can say we can calculate displacement caused by unit load in place of RB. And if we do that, but because after I change the approach to doing the concept first, I've seen some students would rather calculate the displacement caused by RB. They are more comfortable with that. It's the same thing. Now, when you calculate the displacement caused by the load that is equal to 1, you will get the displacement. At this time, generally, I think the nomenclature, they call it delta small b, and there are two b's, to indicate that this unit load is applied at B, and we are calculating the displacement at B. Okay, there are more to that, and we will come back and maybe discuss why we have to be here. Okay, but now this is caused by the load that has a magnitude equal to 1. So after you know the displacement caused by the load that is equal to 1, what would be the displacement caused by the load that is equal to RB? Do you believe in the linear relationship? Of course you do, because one big thing that has been said long time ago up to this point is that you must live in the elastic world. The inelastic world means that you are here, right? In your stress-strain relationship, you are in this very elementary region of the behavior of the material. Meaning, if your load here is equal to 1, and it gives you delta BB, and you increase your load to RB, everything is proportionate. So here is going to be equal to delta BB multiplied by RB, right? Because it's linear. But if it's not non-linear, ooh la la, you can still do it. Some extra equations, correct? So if unit causes displacement equal to delta BB, then RB will cause the displacement equal to RB delta BB, which is essentially the same thing. If you go on and calculate the displacement due to RB in that term, you will have the RB in the displacement. But if you don't want that, you can use 1 and then multiply by RB later. It's the same thing, because a few days back, my son asked me to play the jigsaw with him. It's a 500 piece jigsaw, and generally we spend like 4 hours. Is it? And then I started saying about the I would love to have 1,000 piece jigsaw. He said, let's do it. If a 500 piece jigsaw can be done in 4 hours, doesn't mean that 1,000 piece can be done in 8 hours. No, because it's not linear. The relationship between the time that you spend completing the jigsaw is not linear with the number of the jigsaw you have. It's exponential. Because 500 pieces, you can do it in like 4 or 5 hours, but 4,000 takes weeks. Just shoots up. But here, you have a linear relationship. Okay, so you can do it. So number 4 here, we can say, I can do both, just to show you. Okay, so let's say I'm gonna do this. Let's say 1. Okay, now we are going to do the same. Delta BB is again TBA. Okay, so it means that I'm gonna have to draw the bending moment diagram. Whoops. Okay, and here is how much? It's L, right? Yeah, this load is 1. So TBA is going to be equal to the area. The area is a half of L multiplied by L, right? And now we take moment with respect to point B, which is now 2/3 about. So here delta BB becomes over EI as well. The height is L because 1 multiplied by L over EI. Okay. So L over EI. So it is L square. If you wanna put the unit load there, then you will help you clarify things. L square over 2EI multiplied by 2/3 of L. So here we go. It's L cubed over 3EI. Okay, that is the displacement calculated based on the unit load. Now I know the load equal to 1 gives me that displacement, and as a result, RB gives displacement equal to RB multiplied by the displacement caused by the load that is equal to 1. Excuse me, it looks really ugly. Okay. Or my beam also looks ugly. If I say this is RB, now my bending moment diagram here becomes RB multiplied by L, right? And divided by EI. And delta B is going to be this area. The area this time is going to be equal to a half of the base length, that is L, and then RBL over 2EI. Okay, so here it's therefore RBL square over 2EI area multiplied by again the same moment arm, third length, and turns out to be the same thing. RBL cube over 3. Notice that in both cases we have RB in the equation. So from here, we can establish compatibility. And notice that one more thing, I'm pretty casual with this because I know what it is. In the calculation of this displacement caused by this, actually moment diagram is negative. So this value is in fact has a negative value to it. Okay, so I can put this minus WL to the power 4 over 8EI. That's a displacement caused by the uniform load. Negative here represents the downward direction. And then this is the upward direction. So it's plus RBL cube over 3EI equal to 0. That is the compatibility equation. And now we know everything except RB, and you can obtain RB from this. Okay, so RB is equal to WL to the power 4 over 8EI multiplied by 3EI over L cube. This is gone. This is 1 now. EI is gone. So you see, it's 3WL over 8. It's not half anymore. because your reaction for the first time in your life will depend on displacement. What is the function of displacement? Part of displacement depends on EI, the material that you use, and the property of your cross section. See? Because calculation now involved displacement. Reactions are now dependent upon material and section properties. This is the major issue of the indeterminate structure. For the determinate structure, you can calculate everything without caring about properties like B. No. You can always calculate moment in your simple beam, in your cantilever beam, without knowing how much the moment of inertia of your cross section is, or without knowing how much the modulus of elasticity is. Now, if we change EI, your reactions will change. That is one major knowledge of the indeterminate structure. If you change your properties, reactions will change. Okay. Now I can do the same with this, but let's say the point is just to try to give you the concept first. So let's come back here and take a look at this condition. It's the same, okay? If we have the indeterminate structure like this, now you know you have 1, 2 reactions here, 3 and 4 reactions. By removing one, you have a simple B. By removing RB, you have a simple B, but you have the displacement. So in this case, if I am going to repeat this again, this is L, this is L. This is your continuous beam with, you know what? Let me go back here a little bit. This is step number 4. We've done step number 4, right? You get step number 4. 1, 2, 3. I should complete this. Here is step number 5. Compatibility. Now you're done. Okay. Here, let's back here. So step number 1 again is to determine the type of structure that we have. So it's again indeterminate structure with 1 degree of redundancy. Okay. And now step number 2 is to create the primary structure. Oops. And now you have displacement. Okay. Step number 3 is just to calculate this delta. And step number 4. Remember, step number 3 has the external load on it. It's the displacement caused by the load. But step number 4 is the displacement caused by your reaction. It's better. Calculate delta. And step number 5, compatibility. Okay, here plus here equal to 0. Okay, so that's the idea of the solution to the indeterminate structure. We call this the method of consistent deformation. So as we can now, down here. Yeah, the method of consistent deformation, or simply put, it's the force method. Okay. So I'd like to give you more ideas. Not this one. Okay. Why? Why they become smaller again? I don't understand program at all. Sometimes give me a big page. Let us. Oh, damn it. They're so inconsistent, right? They don't use the method of consistent deformation. Cool. Okay. Right. So likewise, we need to establish the concept first. And you will see, after you understand, after you see the big picture, what you need to do, the next step, we're going to have to go back and say, underline the fact that you can actually calculate displacement. Okay. I have just used one method, that is the moment area, which you have learned. But in this case, you know, maybe the more useful ones would be the virtual. So let's say if again we have a frame. You know, the typical one is just to turn things into hinges on both sides, small, typical. Okay, and now you see, after the one calculation that we've done, that here, let me underline. Okay, maybe here. From this, say this is W, this is L. From the calculation, it shows that this reaction is 3/8 WL, and this is 5/8 then, right? Because that's 3/8, so this is supposed to be 5/8. You see, you can never ever solve this kind of structure by, okay, take the moment. It's impossible. And you see, they're not equal anymore. It's 5/8, 3/8. You could never ever obtain this by any other method, other than the methods that can be used to solve the indeterminate structure. So let's say if I give you something like this. Okay. Maybe you say, hey, it's equivalent. I mean, it's a symmetric structure, so you could guess maybe the sigma fx equal to 0. It could be half. Yeah, half. It's of the nature of the structure. But let's say, make the method put on model. If it's impossible, you cannot assume that your base horizontal reactions is going to be equal anymore. Okay? So, what if you face something like this? What do? Same concept, isn't it? Why so much? All right. So here, it means that we, again, first step is just to determine what kind of structure do we have. So how many reactions do we have? 1 and 2 and 3 and 4. 4 reactions again. So we have 3 equilibrium equations. So that means this is 1 degree of redundancy, right? Coming from 4 minus 3, 4 unknowns, and 3 equilibrium equations. So now we need to create the primary structure by removing one of the redundants. Okay. Now it seems like this is where you maybe should not be so creative in removing the redundant. But some students are maybe sometimes very creative. Say you have a choice, because let's say if I let's call this HA, okay? RA, and I like the ABCD in that way, so let's call this HD, not high definition, the horizontal reaction of D, and then RD. Well, I can remove HA. When I remove HA, I have this. Let's say HA remove. And or I can remove HD. Right? But some, I think this looks natural, okay? But some would, for example, we're gonna do that. I wouldn't do that, would I? Would you? I think it's still under equilibrium, but you are giving yourself a very weird thing to solve. You may try, if you're curious, if it still works, it's just the same. I say it probably is going to work, but chances are you're going to mess up your moment because you are not familiar with this kind of structure. Like this, for example. A cantilever beam with the roller. By the way, this is called prop cantilever. Okay, the typical structure that you will see a lot in your foundation or soil mechanics stuff. Instead, I think the easiest way to remove the redundant is to remove the roller, because you have a cantilever beam, and the calculation of displacement in cantilever beam is very easy, to say the least. But you can go like this, okay? You can go like, you can remove the moment, yes, like that. Remove the moment to have a simple beam. It's okay. But some would be, yeah, let's remove the reaction. The question is, can we do that? Absolutely, you can. But do you know what you're dealing with? That's the question. You can remove reaction a day, but what you have is the support that can take moment, but not the vertical reaction. Do you know what that is? If you remove RA, you have the roller, correct? But then this roller can take moment. It becomes something like that. We call this a shear release. You can do that, yeah. But can you handle it? Okay. No shear, but yes, moment. So your choice is important. Okay, anyway. So let's say you remove this. If you remove HA, you will have the corresponding displacement. That is going to be horizontal displacement at A. And your structure would go like this, maybe. Should be equal. Okay. So that, if you remove HA, you will have displacement at A in excuse me. Maybe I'll change the size again at A in horizontal direction. This close. It's going to be a little bit more difficult to draw here, but anyway. If you remove HD, you probably have something like this. Okay. That's HD. Delta at D in the D in the horizontal direction. So we need to find a way to calculate those qualities. Okay. And once you have your primary structure, you can calculate this. And then again, you will this is useful, but it's inalytic. Okay. Anyway, step number 2 and 3, right? This is step number 3. You calculate this. Delta A H or delta E H. And then step number 4. Let me move this, okay? Step number 4, we calculate now remember one more thing. When things get complicated, you must get your basic right. You remove HA in the first case or HD. When you remove HA, you will have to deal with horizontal displacement at A. Nothing else. This is another grave error that students make. You remove whatever redundant, you calculate the corresponding displacements of that redundant. Okay, it's not like, okay, I remove HA and now I'll calculate delta D. No, if you remove HA, you will have to, you have this, right? And then you will apply the unit load there. And then calculate, here is delta A, if it's a unit load, say, if it's a unit load, I should call it delta AA, right? Then multiply by HA. Oops, I don't need to calculate delta AA. Okay? or delta DD if you choose to remove HD. And sorry, this is going to be your other case. Doesn't matter where you want to apply that. Okay. And then step number 5 is to write your compatibility. That would be delta AH plus delta AA, but this is due to unit load, so I have to multiply by HA, right? Equal to 0. Or delta DH plus delta DD multiplied by HD equal to 0. Okay? Get the concept right. This is our target of the indeterminate structure. We need to be able to establish the compatibility condition. Okay? And in order to establish compatibility equations, we need to be able to calculate displacement, deflection, so and so. So I think with that, one more thing. Notice that this compatibility equation is one extra equation that we are looking for. Remember, from these examples, we have 4 unknown reactions, correct? So it means we have one unknown greater than the number of equilibrium equations. In order to solve for unknowns, we have 3 equations. So basically, we need to find one extra equation. In that case, if we have 4 unknowns and 4 reactions, we can solve it, right? And this is your 4th equation. The compatibility equation is your 4th equation. Okay? So with that, we're gonna take another break. And yeah, this second break is gonna be 15 minutes long. And that means we are going back here again at about 11:36, something like that. Okay, is there any question? I suppose not. So let's take a break.